Biodiversity is everywhere, from the more well-known communities like coral reefs and tropical rainforests to what we've learned like alpine deserts and lakes. You can find biodiversity in every community on Earth. You can even find it in outer space, because we all know that aliens are a thing. So how do you measure biodiversity? Well, you look at species diversity, or D, the definition of which can be found here. And it's also really important to remember that D has two aspects, richness and evenness. Richness is the number of species present in an area, so how many species you actually counted in your sample, while evenness looks at how abundant each species is. So if you found 10 species, each represented by 5 individuals, you would have a very even sample. Now when estimating biodiversity, it's often underestimated, and this is due to the species accumulation curve. The curve essentially says that the number of species found will increase as the sampling effort increases. In the graph here, the sampling effort is represented by the number of monthly samples, but it can be represented by a number of different factors. So there are 3 different levels of biodiversity. There's alpha, beta, and gamma. And a really good way to conceptualize this is through a same technique as a really good way to conceptualize a lot of complex problems, Disney movies. So we're going to be looking at The Lion King. And in The Lion King, you have your main group of characters, Rafiki, Simba, Mufasa, Timon, Pumbaa. And then you have a secondary group, kind of all the animals that the lions rule over. So within that main group, you have your alpha diversity. And then between the main group and the secondary group, you have beta diversity. Gamma diversity is when you put the entire movie together. The Lion King also unfortunately taught us, in one of the saddest scenes ever, that disturbances can occur to communities. These disturbances are measured in 3 ways, through scale, frequency, and intensity. So you can have a really small disturbance, like a single tree falling, or a massive disturbance, like the earth blowing up. So the intermediate disturbance theory essentially says that in order to maximize diversity, you want semi-frequent, middle intensity, medium-sized disturbances. If disturbances are too big, too frequent, or too strong, or too weak, too infrequent, or too small, you're going to get a decrease in diversity. How a community responds after a disturbance is due to something I like to call the bowling ball theory. So essentially, if you have a disturbance, a bowling ball will start to roll up the hill in a valley. If the disturbance isn't strong enough, the bowling ball will settle back in that initial valley, and the stable state will remain the same. If the disturbance is strong enough, the bowling ball will roll up over the hill and into a new valley. This represents the community needing to establish a new stable state. One prevalent theory about why this happens and why communities are able to recover is the redundant rivet theory, which essentially states that the ecological function of many members of a community is redundant, and therefore you can remove multiple members before you see an impact. But if you remove too many, well, the community is permanently changed and you need a new stable state, just like this airplane.
Alright, so primary productivity and nutrient cycling. So basically, the Earth, like most other biological systems, likes to maintain a kind of state of homeostasis, and it can do this by changing the fluxes between different storages of different nutrients, which is nutrient cycling. And you can also see this in its cycles of autotrophic production or primary productivity, which then makes up the bottom of most food webs and food chains. All right, so the carbon cycle is really important because carbon dioxide is a greenhouse gas, which has a really big effect on global warming patterns, which has a number of ecological and biological effects throughout the planet and obviously impacts our daily lives a lot. So carbon dioxide is stored generally in 3 places. It's in flux as a gas in our atmosphere and within our waters. Consumers and producers also give off carbon dioxide through respiration. Primary producers also use it through photosynthesis, so those are also within a flux of each other. And they also can both become detritus, which is dissolved organic carbon, or particulate organic carbon. Marine snow can remove some of it from our waters, but overall, there's not that. But overall, it doesn't take away that much of it. And overall, atmospheric carbon has increased upwards of 30% from pre-industrial time. So we're having a big impact on these fluxes and changing them, which is why it's resulting in issues. If you look at the Keeling curve, you can also see the general increase of carbon dioxide concentration within our atmosphere over a relatively short period of time. And within this, you can also see the natural smaller cycles of carbon dioxide increasing and decreasing as our Earth goes through cycles of primary productivity.
Nitrogen, which makes up much more of our atmosphere, begins as N2 in the atmosphere. However, this form of nitrogen is not able to be used by organisms and must be fixated first. This is typically done by lightning and bacteria through processes such as nitrogen fixation, ammonification, and nitrification. Once fixed, primary producers can absorb the nitrogen. After being taken up, primary producers can excrete the nitrogen back into the nitrogen pool, die, become detritus, or be taken up by consumers. Like primary producers, consumers can also excrete nitrogen back into the nitrogen pool, die, or become detritus. The death of both consumers and producers results in nitrogen loss. Additionally, detritus that is not decomposed back into the nitrogen pool is lost as marine snow, which results in nitrogen loss. The only way to recover this loss is through So how much have humans altered the nitrogen cycle? Overall, humans have more than doubled the nitrogen input into terrestrial marine ecosystems through processes such as rice cultivation, land clearing, draining of wetlands, burning of fossil fuels, forest burning, and animal emissions. Phosphorus, unlike nitrogen, does not have to be fixed first. It's dissolved into marine systems mainly through dust storms and seabird input. Once dissolved, phosphate can be taken up by primary producers and consumers, but can also be excreted by them. Additionally, phosphate can be transferred to consumers through the eating of primary producers. Likewise, both primary consumers and producers can lead to a loss of phosphorus if they don't become detritus. Detritus that doesn't decompose and re-enter the phosphorus pool becomes marine snow, and this results in a one-way loss of phosphate due to transformation into sediments. Humans add on to the phosphorus cycle through phosphate mining and fertilizer. These fertilizers can run off into water sources and promote net primary production. In excess, however, this can lead to eutrophication, which is definitely not good. Overall, anthropogenic effects have led to an increase in carbon, nitrogen, and phosphorus. This alters all three cycles and leads to climate change, which is definitely bad, because climate change plays a major role in biodiversity, food security, health, and water.
We're about to interview some gym buffs about evolutionary ecology. So let's go. What is the latitude of a system? I have no idea. That's okay. What is the latitude of a system? What is the latitude of a system?
Of a system?
Yeah, the latitude.
The latitude?
Word latitude.
Like the coordinate?
It's not the coordinate, it's something different. What is the latitude of a system? What does that mean?
Like longitude and latitude, it's like that line across diagonals. Yeah.
Okay, yeah. What defines a resilient system?
Something that can survive.
Stand by itself? Yeah, right?
What impact on an ecosystem is the mountain pine beetle infamous for?
Is it positive or negative effect?
A little bit of both, but mostly negative.
Oh, okay.
Like, we're seeing it as negative in society.
Does that have to do with trees?
Yeah.
I guess like eating that trees. Eat away at trees. They eat a lot of pine cones.
What is the difference between the way autogenic and allogenic engineers change the environment? Yeah.
One probably has to do with nutrients, the other one probably has to do with like layout.
Okay, sure. I totally knew this sophomore year of high school, but how do the attacked trees fight back?
I don't know.
No idea.
How do the pine needles?
Pine trees, how do they fight back against
They make their roots poisonous or something?
Poisonous in their sap or something. Problems like that.
Kind of, yeah. They like release a sap to it. What is the definitive factor that determines coexistence versus outbreaks in the mountain pine beetle system?
I don't even know what a mountain pine beetle is, so I can't answer that question.
Okay, well, thank you.
Awesome. How many numbers of pine cones you have?
Okay.
Coexistence is when the pine beetles can survive but not thrive too much, where they kill all the trees.
No idea once again. That's totally cool. That was all I had for you, but thank you so much. Yeah. I'm sorry you had to go through that. It's perfectly fine.
Hi, my name is Professor Smith, and today I will be talking about keystone species and community structure.
Hi, my name is Teresa, and I'm a freshman at Keystone State College. Oh my god, what a cute beaver! What are keystone species?
A keystone species is a species that an ecosystem is largely dependent on.
So what will happen if we don't have a keystone species? Like, what if it disappeared?
Without a keystone species, there would be chaos. The ecosystem would collapse.
Leading to less biomass, abundance, and productivity. Look, the kelp bed has been invaded by sea urchins. Ah, Professor, why are keystone species important?
Keystone species are important because they help control the number of organisms within each species in an ecosystem. They do this through top-down and bottom-up control. In top-down control, predators prevent the overgrowth of a prey species that would otherwise get out of hand. This is why you saw so many sea urchins after the removal of the otter. In the bottom-up control, keystone species provided food sources absolutely necessary for the other trophic levels to survive. You need kelp to sustain the sea urchin and otter populations.
So this graph is basically showing that we also need to control the number of keystone predators, because even though it's good to have a certain number, once we go out of that range, diversity will start to decrease. Predators will eliminate competitors as well as all the prey. Oh, and eventually that will lead to their own demise, since no food equals no predators. I've also heard about foundational species. Can you explain how these differ from keystone species?
Foundational species are dominant in abundance, biomass, and productivity. They aren't the center stone of the ecosystem arch per se, but they are the foundation upon which the arch is built. The trees and coral here all give physical structure to the ecosystem. One example of a keystone species working in an environment is that of the Arctic sea ice algae. Without this algae, the ecosystem would collapse. The sea ice algae is on the T1 trophic level. It is then consumed by the T2, T3, T4, T5, and T6, the apex predator.
But the food chain is not one of the only ways in which mankind has used the ecosystem to its benefits. Humans do make up T6, the apex of the trophic web. However, I've also heard about animal sentinels. Can you explain about that?
An animal sentinel is an animal that is used to monitor the health of an ecosystem. It will show changes in the ecosystem through disease, toxins, or climate change. Early warning signs from animal sentinels are bioaccumulation, increase in the concentration of a chemical agent in an organism over time, and biomagnification. A pollutant will biomagnify if it is long-lived, mobile, and fat-soluble.
Wow, what a huge effect these animal sentinels have. I wrote a poem about animal sentinels. A dog, bird, perhaps even fish and rose, testing for the safety of a habitat no one knows. Between the extremes of sensitivity and endurance shows, wherever one needs it, there it goes. Braving the infectious disease, climate change, and toxin flows, to whom appreciation mankind owes.
Thank you!
Thank you!
Hey guys, we're going to be talking about field methods in ecology today.
Diversity and abundance are, as Randy puts it, the bread and butter of ecology.
We use field methods to gather data on a species, population, community, or ecosystem level.
Ideally, we use a census to measure the entire population. Techniques such as walking in a grid or radial pattern are typically used to census. When census data cannot be acquired, a subsample can be used.
The following are some tricks on how to subsample.
Trick number 1. Learn how to randomize. Techniques such as choosing numbers out of a hat will reduce bias and the effect of chance.
Trick 2. Learn how to identify organisms. A simple yet helpful way to identify organisms is by using the dichotomous key. Trick 3. Know how to use your body to take measurements. Be resourceful and use what is around you to help in determining data measurements. You could use your finger width, pace, or wingspan to measure, and compare these lengths with a known length, such as the height of your phone or the length of a piece of paper that you might have on you while you're in the field. Trick 4. Be able to count quickly and efficiently. Hand clickers are very useful and do the counting for you. However, not everyone has hand clickers. With practice, visual bins and percents can be a good way to estimate the number or percent of organisms in an area.
Trick number 5. Learn how to use a transect tape. Transects are lines made with either string or tape placed along the area with a systematic sampling is done. The tape needs to be laid out straight and even, and the rules for how to include the subpopulations should be written out in the beginning. Transects are great for sampling areas in which species transitioning occurs as environmental conditions change. Trick number 6. Learn how to use quadrats. Quadrats are used to investigate the distribution of species. You can use either a square quadrat frame if you're determining population densities, or a subdivided quadrat frame for determining the percent cover of species.
Trick 7. Combining transects and quadrats. Usually both transects and quadrats are used for investigating distribution within sessile communities.
Trick 8. Question yourself. Make sure you know what questions you are trying to ask. Determine the design of your random sampling method and field techniques. Trick number 9. Match the method to your question. For example, if you're in the rocky intertidal shore and you want to measure average density in the region, in this case you could use both transects and quadrats like you do in trick number 7 to have strategically placed quadrats along a transect to measure the biodiversity as you go away from shore.
Trick 10. Be able to visualize your data by presenting them in appropriate graphs, tables, plots.
Conservation ecology is the preservation of existing habitats and biodiversity. This includes climate change, mitigation, and preservation of endangered species.
Some assumptions of conservation biologists are that biodiversity is critically important. People use domesticated and wild species for food, fuel, medicine, and various things, and humans depend on their ecosystem service such as water, soil, and climate regulation. Some threats to biodiversity include habitat degradation, which are changes that reduce quality of habitat, such as agriculture, pollution, and deforestation. Invasive species, such as the Guam brown tree snake that you see to your left, that has caused the extinction of 31 native species in Guam, and overexploitation.
Why should we care? Well, we're a part of the planet. Nature doesn't need us, we need it. Loss of ecosystem processes results in loss of ecosystem services. Biodiversity is a measure of the probability of species present with important traits. For example, nitrogen fixers, pollinators, and keystone species. Biodiversity is declining globally, and species are becoming extinct at an alarming rate.
Speaking of extinction, did you know that the average species lifespan used to be 1 to 10 million years? However, the current extinction rate of mammals and birds is only 10,000 years. A perfect example of how humans have increased the extinction rate is the Pyrenean ibex, which was once abundant in the 14th century, but due to overhunting and disease, went extinct in 2000 due to lack of conservation efforts.
However, it's not all bad news. There are some success stories in conservation efforts. What you see here is the Hawaiian brigamia on the left and the New Zealand cockapoo on the right. Both species were rescued from near extinction using conservation tools that we will later discuss.
And to have more of these success stories, scientists need to actually know what endangers these species. And an important concept to know is that different biomes face different threats. If you look at the chart below, you can see that each threat affects the various biomes to different degrees.
Some examples of conservation tools are the precautionary principle and PVA. The precautionary principle is a guide to taking actions now that help prevent future consequences or detrimental effects to the environment and its inhabitants. Population viability analysis, PVA, allows ecologists to assess extinction rates to determine the extent to which conservation measures should be taken. An example of population viability analysis was with the California condor. Direct intervention was used because of the extremely small population size. The condor was removed from its natural habitat and bred in sheltered conditions. Over 200 birds were bred, and some were even released into the wild. Unfortunately, this is extremely expensive, so it cannot be maintained.
Another conservation tool used by ecologists is prioritization. This is a way of categorizing species within a community to more efficiently allocate resources to maximize biodiversity. The species categories include flagship species, which are charismatic organisms that people will want to protect, surrogate species, which is when protecting habitats for one species can result in protection for other species, umbrella species, which are species that shield other species with similar habitat requirements, indicator species, which are used to assess the magnitude of disturbance, and focal species, which are most sensitive to a threat in a changing environment.
That's all, folks. Thanks for listening.
Emily and Austin, signing off.
Signing off.